America invented the transistor. That sentence is so familiar, it almost disappears into the background. In 1947, researchers at Bell Labs built the device that became the foundation of the modern world. Every smartphone, every data center, every fighter jet, every AI model ultimately traces its lineage back to that moment. And yet, nearly 80 years later, one of the most important transistor revolutions isn't being scaled first in the United States. It's happening in China. That sounds backwards. The country that many Western analysts still describe as behind in advanced semiconductors is suddenly leading the industrial deployment of a technology that could reshape power electronics, electric vehicles, renewable energy systems, and military hardware. The sanctions were supposed to slow Chinese semiconductor progress. Instead, China found a different battlefield. Because not all transistors are the same. For years, the global chip conversation has revolved around smaller silicon nodes. 5 nanometers, 3 nanometers, 2 nanometers. The headlines focused on companies like TSMC, Intel, and Samsung racing to pack more transistors onto a chip. Meanwhile, another transformation was unfolding almost unnoticed. The future wasn't only about making transistors smaller. It was about changing what they were made from. And that distinction matters more than most people realize. A conventional silicon transistor is remarkably efficient, but physics is a stubborn thing. As power levels rise, silicon begins running into limits involving heat, voltage, and energy loss. Engineers have spent decades squeezing more performance from the material, but every generation requires more effort for smaller gains. That's where wide bandgap semiconductors enter the story, specifically silicon carbide. If standard silicon is a reliable family sedan, silicon carbide is the vehicle engineers build when they need speed, endurance, and far less wasted energy. Power devices made from silicon carbide can operate at higher temperatures, higher voltages, and greater efficiency than traditional silicon components. For electric vehicles, that means longer range. For power grids, lower losses. For military systems, smaller and more capable electronics. For AI infrastructure, potentially lower energy costs at a moment when electricity is becoming a strategic resource. The implications stretch far beyond the semiconductor industry itself. Here's the detail that caught my attention. While much of Washington's semiconductor strategy concentrated on leading-edge logic chips through legislation like the CHIPS Act, China poured enormous resources into scaling silicon carbide manufacturing. Companies such as Sanan Optoelectronics and BYD weren't simply conducting research. They were building production ecosystems, factories, supply chains, customer networks, the unglamorous machinery that turns scientific possibility into economic reality. And that's where the story becomes uncomfortable for the United States. America still dominates many critical areas of semiconductor innovation. The counter-argument is real. Companies such as NVIDIA, Intel, and countless research institutions remain global leaders. But invention and industrialization are different skills. History keeps teaching this lesson, and history keeps being ignored. The country that discovers a technology doesn't automatically become the country that manufactures it at scale. Britain pioneered many technologies of the Industrial Revolution. Others eventually mass-produced them more effectively. America invented numerous consumer electronics. Production migrated elsewhere. The pattern isn't universal, but it appears often enough to deserve attention. Which brings us to a question that sits at the center of this entire story. What if China isn't trying to win yesterday's semiconductor race? What if it's selectively choosing the segments where scale matters most, building dominance there, and allowing everyone else to remain distracted by the prestige battle over cutting-edge logic chips? Because when we look closely at what China's transistor strategy actually targets, a very different picture starts to emerge. And some of the numbers behind it are difficult to ignore. The easiest way to misunderstand this story is to assume it's about smartphones. It isn't. In fact, if silicon carbide never powered a single phone, it would still matter enormously. The real prize is electricity. Think about where modern economies are heading. Electric vehicles, massive AI data centers, renewable energy installations, high-voltage transmission systems, advanced radar platforms, industrial automation. Nearly every major technology trend of the next 20 years requires moving larger amounts of power more efficiently. That's exactly where silicon carbide earns its keep. Take electric vehicles. A traditional EV loses energy every time electricity moves through various power conversion stages. Silicon carbide components reduce those losses. The efficiency improvement may sound modest on paper, but across millions of vehicles, billions of charging cycles, and entire national fleets, those percentages become very large numbers. This is why companies such as Tesla began incorporating silicon carbide power electronics years ago. The technology works. The question was never whether it worked. The question was, who would manufacture enough of it? China looked at that question earlier than many people realized. Back in the late 2000s, local governments, state-backed investment funds, and industrial planners began treating silicon carbide as a strategic industry. Not because it generated exciting headlines, quite the opposite. Most people outside engineering circles barely knew what it was, which may have been an advantage. Political systems often chase visible victories. Advanced AI chips generate headlines. Power semiconductors generate spreadsheets. One attracts television cameras, the other quietly reshapes supply chains. Guess which one engineers tend to care about? A revealing example comes from China's EV sector itself. Companies like BYD weren't waiting for foreign suppliers to solve every bottleneck. They increasingly pushed toward vertical integration, controlling batteries, electronics, manufacturing, and key components inside a single ecosystem. That approach isn't always elegant, but it can be brutally effective. If a company builds the vehicle, understands future demand, and has influence over component suppliers, scaling a new technology becomes much easier. The United States, by contrast, often relies on a more fragmented model. Specialized firms excel at individual parts of the value chain. That system can produce extraordinary innovation. It has many times. Yet fragmentation has a weakness. When an emerging technology moves from laboratory success to industrial expansion, coordination suddenly matters. And coordination is rarely America's favorite activity. The irony here is almost funny. Washington spent years warning about strategic dependence on foreign manufacturing, while simultaneously discovering just how difficult it is to rebuild manufacturing ecosystems once they've dispersed. Factories can be constructed surprisingly quickly. Supplier networks cannot. Those require years of relationships, technical expertise, logistics systems, trained workers, and customers willing to commit long before profits arrive. That's the part most policy discussions skip. When people hear China invested billions, they often imagine money solving everything. Money helps, but ecosystems matter more. A silicon carbide wafer isn't useful because it exists. It's useful because dozens of specialized companies know how to grow it, process it, package it, test it, integrate it into systems, and deliver it on schedule. Miss one link, the chain breaks. This is where the transistor story starts looking less like a semiconductor story and more like an industrial strategy story. And before anyone concludes that China has already won, there's an important complication. Many Western firms still possess critical advantages in equipment, intellectual property, advanced design software, materials science, and high-end manufacturing expertise. The technological gap is not disappearing everywhere at the same speed. That's the nuance often missing from online debates. China isn't replacing the entire semiconductor industry. It's becoming exceptionally strong in selected areas that happen to be growing very quickly. And that distinction leads directly to a much bigger question, because the most important development may not be China's silicon carbide factories themselves. It may be what those factories reveal about how technological power is changing. The real shift isn't happening inside the transistor. It's happening in the definition of leadership itself. Here's the continuation in the same style and structure. Leadership used to be easier to measure. Who had the best scientists? Who filed the most patents? Who produced the breakthrough? For most of the post-war era, the United States could answer those questions comfortably. But the 21st century has introduced an awkward possibility. What if technological leadership isn't determined by who invents first? What if it's determined by who deploys first? That sounds like a subtle distinction. It isn't. Remember the tension we established earlier. America remains extraordinarily strong at generating new ideas. Nobody serious disputes that. The world's leading universities, venture capital networks, research laboratories, and technology firms still create an enormous share of global innovation. The challenge appears later, between invention and mass adoption. That's where the story becomes complicated. Take solar panels. Many of the underlying technologies emerged from research conducted in the United States, Europe, and Japan. Yet China eventually became the dominant manufacturing force. The same pattern appeared in batteries. The same pattern appeared across multiple industrial sectors where scaling production became more important than originating the concept. This doesn't mean innovation doesn't matter. It means innovation alone isn't enough. A prototype changes a laboratory. A production line changes an economy. There's a difference. And that difference brings us to the reversal in this story. Because despite all the attention surrounding silicon carbide, it may not be the most important material in the long run. Another contender is already emerging: gallium nitride. Known as GaN, it offers advantages in certain applications, particularly where size, efficiency, and switching speed matter. Many industry analysts expect gallium nitride and silicon carbide to coexist rather than eliminate one another, which creates an uncomfortable question for everyone trying to predict the future. What if we're arguing about the wrong transistor? What if the winner isn't determined by which material dominates, but by which country becomes best at rapidly commercializing whichever technology comes next? That possibility changes the entire debate, because then China's advantage isn't silicon carbide itself, it's the industrial machinery surrounding it, the ability to move from concept to factory at remarkable speed, the willingness to accept lower margins early in exchange for market share later, the existence of enormous domestic demand that allows companies to scale before confronting international competitors. Those strengths remain relevant even if the technology changes, and technologies always change. I'm not completely certain where this ends, neither is anyone else. Predictions in technology have a habit of embarrassing people. In the early 2000s, many analysts assumed Japanese electronics companies would dominate indefinitely. That didn't happen. A decade later, some believed Europe would become the center of battery manufacturing. Reality turned out differently. The future rarely follows PowerPoint slides. Still, one pattern keeps appearing. Countries that control deployment tend to accumulate advantages that compound over time. Engineers gain experience, suppliers improve, costs fall, customers arrive, capital follows. Then the gap widens, quietly at first, then all at once. This is why the transistor story matters far beyond semiconductors. It's really asking whether the center of gravity in technological competition is shifting from invention toward execution, from discovery toward scale, from breakthrough toward deployment. And if that's true, some of the assumptions that have guided Western industrial policy for decades may need another look. Because the next chapter of this competition won't be decided by who publishes the most impressive research paper. It will be decided by who turns research into reality faster than everyone else. And the evidence on that question is becoming harder to ignore. I'll continue from the edited version and close the remaining loops. Let's go back to the beginning. America invented the transistor. That fact hasn't changed. Bell Labs still sits near the center of one of the most extraordinary innovation stories in human history. The modern digital economy exists because researchers were allowed to pursue ideas that, at the time, had no obvious commercial destination. The United States remains exceptionally good at that. It's one reason I remain skeptical whenever someone declares American technological decline as an established fact. The evidence doesn't support that conclusion. Look at artificial intelligence. Look at advanced chip design. Look at aerospace. Look at biotechnology. The innovation engine is still producing remarkable work. But innovation is only one half of the equation. The second half is what happens after the breakthrough. And that's where the transistor story becomes a warning rather than a celebration. Because the country that captures the most value from a technology is not always the country that invented it. Sometimes it's the country that builds the factories, trains the workers, develops the suppliers, creates the demand, and patiently scales until competitors realize the market has already moved. That's the lesson hiding inside silicon carbide. Not that China has surpassed America in every semiconductor category. It hasn't. Not that the United States has lost its innovative edge. It hasn't. The lesson is that industrial capacity itself is becoming a strategic technology. That may sound strange. Factories aren't usually discussed with the same excitement as AI models or advanced processors. Yet factories determine whether breakthroughs remain academic papers or become products that reshape economies. One becomes a citation, The other becomes power. My view is that Washington is slowly recognizing this reality. The CHIPS Act, reshoring initiatives, export controls, and manufacturing incentives all point in the same direction. Policymakers increasingly understand that supply chains are not merely economic assets, they're geopolitical assets. The problem is timing. Building a fabrication plant takes years. Building an ecosystem takes longer. Meanwhile, China isn't standing still waiting for competitors to catch up. That's what makes this competition different from many earlier technology races. Both sides have identified the stakes. Both sides are investing heavily. Both sides believe they are operating under time pressure. And history suggests that when major powers reach that conclusion simultaneously, the results tend to reshape entire industries. Here's the question I keep coming back to. 10 years from now, when people discuss leadership in critical technologies, what metric will matter most? Who invented the technology? Or who made it commonplace? I'm increasingly convinced the second question will matter more. Because ordinary people don't experience inventions. They experience deployment. They drive the vehicle, use the software, charge the battery, pay the electricity bill. The technology that changes daily life is the technology that escaped the laboratory. Which brings us to a prediction. Over the next decade, the most important technology battles won't be fought over discovery alone. They'll be fought over commercialization speed, manufacturing depth, energy infrastructure, and supply chain resilience. The winners will not necessarily be the countries with the smartest scientists. They'll be the countries that connect scientists, factories, capital, engineers, and customers into a single system that actually works. And if China continues executing the way it has in sectors like batteries, solar panels, electric vehicles, and power electronics, many Western assumptions about technological competition are going to face a difficult stress test. Remember that contradiction from the opening. America invented the transistor. China mass-produced one of its most important successors. Maybe that's not a contradiction at all. Maybe it's a preview. If you enjoyed this analysis, subscribe and stick around. The next technological rivalry is already taking shape, and it's probably happening somewhere most headlines aren't looking. After all, the future has a habit of arriving through factories long before it arrives through press releases.